Right, okay, a lot of the stuff in this video is going to mirror what we've just done, or what I've done in the previous video about gravitational potentials. We're going to talk about electric potentials. So in electric potentials, what we've got is, we've got a very similar kind of idea, and it's good to start from the same perspective for the most part, where we've got the force between two charges is Q over R squared. So just remember, this could be two positive charges exerting a force on each other to push each other away, or it could be a positive and a negative charge trying to attract each other, or you could even have negative and negative, again, trying to push each other away. Apologies, I've drawn that the wrong way around. So they'd be attracted to each other. So yeah, we got all those different scenarios there. And again, the equation follows through very, very similarly to how we did the gravitational field equations. In the fact that when we look at this force in an electric field, well, force in an electric field is equal to EQ, which we can rearrange to make more sense. Let me just make sense of that. So E equals F over Q, which is the force per unit charge in a field. So say, for example, this has got an electric field around it, and this one feels a force based on it having a charge in that field, and based on this having a charge. Obviously, in this charged field idea, this is just the charge that that's in the field. So in this case, it's not the charge that creates the field, it's the charge that's in the field, so the force per unit charge. So in that case. So what we're looking at now is, because we've got this F equals EQ term, we can replace that over here with EQ is equal to Q over R squared. Well, we can do a very similar kind of idea to the electric, to the gravitational fields, apologies, where we're effectively saying that there's going to be an electrical potential energy. An electrical potential energy is just EQR is equal to KQ over R squared. Obviously, we've times that both sides by R. That gets rid of that. That gets rid of that. So we end up with electrical potential energy. So we get an electrical potential energy in this field. So I'm going to put electric potential energy is KQQ over R. And look how similar that is to the gravitational version of GPE. Just look, GPE is equal to GMM over R. So look how similar those are all the time. They follow very, very closely to each other, which makes them easier to remember for the most part. So we're still following through the same idea. So same as having an amount of potential energy, a physical amount of energy, as in joules, we can then say, in the case of the gravitation, we had joules per kilogram. Well, here we can change it to, sorry, that's not equals. We can have an idea of joules per kilogram, which gives us VG. We can now say that over here, we can also say we've got an amount of joules per unit charge. Now remember, we can say that it's got an amount of energy per unit charge in this field. So we're saying, okay, what if we didn't know this charge? We'd say, oh, it's got this amount of energy per unit charge. So we've got our electrical potential here. Interestingly enough, the fun thing about electrical potentials is it has another definition. Those of you who are very savvy will notice joules per coulomb already has a unit. It is the volt. The volt is a joule per coulomb, and so actually a potential has the same unit as the volt. It's a volt. So VE in the case of electric fields, electrical potentials are just voltage, which is really, really cool and makes your kind of job a bit easier in your understanding of what it is. So where do we get the equation from then? So remember, it's joules per coulomb. So this is joules at the moment. This is joules. So we need joules per coulomb, so we can divide that by Q. So EPE divided by Q equals KQ over R. And look at that, we've now got a term for VE is equal to KQ over R. So that's potential in an electric field. And that's really, really useful. Now notice, there's no minus sign here. Okay, so most of you, if you're watching this video for the first time, you're going, well, of course there's no minus sign. You just plugged that out of thin air. Well, if you've watched the gravitational potential video before this one, you'll realize that in the gravitational potential equation, there is a negative sign. So Vg is equal to Gm over R, but it's all negative. Okay, so this one doesn't have a negative sign because of the way we define electrical potential in this case. So electrical potential is defined as ElecPot for short. Electrical potential is defined as the work done, okay, against the field per unit charge required to move the positive or a positive charge from infinity to that point. Well, we've seen this definition very similarly before, except there's a slight difference, where work done was done by gravity in the case of gravitational potential. This time, it's work done against the field. Well, what field are we talking about here? Well, the field in this case, because we are talking about this, we have to take this definition from some perspective. We have to give it a definition from a perspective. So, as you may remember, when we were defining what a field does in a radial field, well, the reason we draw these arrows going out is because if we were to stick a positive charge in that field, they would experience a force going away, and that's why we draw the arrows that way round. Well, we had to do some sort of convention there, so we've got to do a convention here just to make it, just to have a solid rule for it. Otherwise, we're all in turmoil. We have riots and looting and all kinds of crazy things. No, I'm only joking. But the idea is that you've got to have some convention for this in order for this to work. So we stick a positive charge in this field in order to move a charge from infinity to that point. We have to do work on it. We have to physically move it from there to there. Whereas in the case of the gravitational one, it was gravity that had to move it from infinity to that point. So the work done is slightly different. So work done against the field because the field is acting in that direction here. So this is work done against the field. And again, we have equations that we can use to represent that work done in terms of very similar equations that we looked at already. So remember we said that electrical potential energy was equal to KQ, that's a G, KQ over R. Okay, QQ over R, apologies. KQQ over R. Well, again, we could rewrite that as Q, I keep writing G for some reason, KQ over R. And look, what's that value? What's this term right here? Well, it's potential. So then we can rewrite this equation to be Q V E. But of course, this is the amount of energy it would have at a point. If I want to know how much energy it takes to move it from a point to point, say either even this point to another point in this field, whether we moved that positive charge at that distance r, then we need to know what the change in potential is. So this is change in potential, change in EPE. Well, that's just work done is equal to Q delta VE. And so we have now an equation that we can use to work out, well, what is the work done when I move this value from here to here? Now, I mentioned before that these aren't necessarily positive, these aren't necessarily negative, because in this case, the force is acting to push it away. So we are having to put work in to do this in order to make this happen. So that means that potentials in a repulsive field are positive. So we can say VE in a positive field are VER positive. No, I'll just rewrite that sentence. How about that? VE are positive when in a repulsive field. Okay. Whereas with a negative field, because remember, you can have, sorry, with an attractive field, because you couldn't have an attractive field here, couldn't you? You could stick a negative charge. Remember, this demonstration is just for a definition of electrical potential. What we're doing here is we're saying, well, what happens if we change things slightly? So VE are negative when in a attractive field. Okay. And that's as far as we'll get with that in this video. So it's just getting you to think about where are all these equations coming from. This is possibly one of the more important ones down at the bottom here, where you're saying work done is equal to charge times the change in potential in an electric field. Same thing in gravitational. There are a few graphs and things we need to look at, but I'm going to do those in another video just to really hammer that home and the specific points that can come out by looking at graphs of potential against this value R and what they look like.